So say whoop, there it is. Whoop, and there it is. Okay, so we are back once again to talk about relative velocity. Now, this is something we talked about earlier on in the year. The idea of you being at the airport and you being on one of those walking magic carpets, and if it's moving you one direction and you walk the opposite, you're really like not moving. Well, you think you're moving, but just with respect to everything outside of you, you're not. That's that idea of the relative velocity. Now, we're going to look at that relative velocity, but within the world of vectors, because when we talked about it previously, we only talked about it like left, right, or up and down. Now we can kind of point in a million different directions, and this is still the same idea, but just how does it work vectorially? So we have this equation here. The relative velocity equation is the velocity with respect from the observer to object A is equal to the velocity of the observer respect to B plus the velocity of B respect to A, okay? Or relative. And that equation, it looks kind of weird, right? You're looking at that and you're like, what am I looking at here? But whenever we break down this example, you'll quickly see what's going on here, okay? And the big thing to just recognize is in this equation, the vectors that you're adding together, because all these are vectors here, the vectors that you're adding together are going to have a linking term here. And in this case, it's B. And what's going to happen is the B's are going to go away, and we're going to be left with just an O and an A, which is what we have here. Okay, so we'll see how that kind of works out in one of our examples here. Now, whenever you're setting something like this up, just draw the triangle. Draw the triangle to what actually makes sense, label the sides of the triangle, and then use your SOHCAHTOA. Pretty much like everything we've done in this unit, it all comes back to SOHCAHTOA or the Pythagorean Theorem in the end. Okay, so let's take a look at an example. Let's kind of break down this equation and just what the heck is going on. So what we have here is a boat being propelled through the water. So a boat's engine propels it horizontally at 1.5 meters per second. The river is flowing at 3 meters per second. What's the velocity of the boat relative to the shore? And we'll give it direction as the angle from the river current. So let's work this out real quick, okay? So if we put this boat on a lake where there's no currents or whatever. It's just like, it's a giant swimming pool lake, stillest, glassiest water you've ever seen. This boat, with respect to that water, is going to have a velocity of 1.5 meters per second, okay? And if we kind of think about that in a different way, this boat is moving down the stream as all the other pieces of water are moving down the stream. So since everything's kind of moving with it, the boat's just with respect to the river at 1.5. So I like to think of it, though, as just, if we put this boat on a glassy lake with nothing going on, the boat's velocity with respect to the river is 1.5 meters per second. So the boat's velocity with respect to the river is 1.5. Okay? And let's just put this like this. Whoop. That's the V, boat, river. Now, the river itself is moving at 3 meters per second. And the river's moving at 3 meters per second relative to, someone standing at the shore looking at it. Like, if you're in the river and you're moving with it, you don't think the river's actually moving. You see the land around you moving, but, if you floated a rubber ducky with you in the river, that ducky would stay with you. Be like, whatever. Okay? So the river's velocity with respect to the shore is 3 meters per second. So when we add to this the river's velocity with respect to the shore, notice now I'm getting this river term in both of these. This means that if I'm adding them, if I add these head-tail method, if I add from the boat respect to the river to the river with respect to the shore, what we're going to have is the resultant boat velocity with respect to the shore. And that's because if we go from start to finish, our boat is going to move towards the shore, but it's also going to move down the river. And that makes sense. Like, as your boat is, coming across the water here, it's also being taken downstream. So, you see your boat kind of like wind up over here. Okay? And if you imagine like swimming across the river, like you get swept with the current and you're going to wind up further down. So that's what's going on here. This right here, this is the equation we built earlier up top. Okay, up top it kind of looks a little weird, but whenever we look at the example, the boat's moving with respect to the river because it's in that water, it's in that substance. the river's moving with respect to the shore. If I add these vectors together, I will get the boat's velocity with respect to the shore. And in this case, since this is a lovely right triangle, and I know this side is 1.5 and this side is 3, if I'm looking for this over here, if I'm looking for the velocity of the boat with respect to the shore, well, I can use a Pythagorean theorem to solve that. If I want to find that with a Pythagorean theorem, I recall that to find the hypotenuse, it's just the a side squared plus the b side squared, and then take the square root of it. So this velocity of the boat with respect to the shore, that hypotenuse, is equal to the square root of 1.5 squared plus 3 squared. And this is going to give me some value. It's got to be at least bigger than 3 because it's the largest side. So 3 squared is 9 plus 1.5 squared gives me 11.25. And then I take the square root of that, and I get that the velocity of the boat relative to the shore is 3.35 meters per second. Okay? So that's all that's going on there. If we wanted to figure out a direction this is going, they ask us in the problem to find it as the angle from the river current. So technically, if our river current is kind of going up like this, they're asking us just to solve for this angle. But if we wanted to give a proper polar angle, we could find this angle on the inside here too. We can do that all sorts of ways. We know all the information possible about this triangle. We know the top sides are 1.5. We know the blue edge is a value of 3. We know the hypotenuse here is whatever we just solved for. Was that like 3.35? So whichever inverse sine, inverse cosine, inverse tangent you want to use to solve for this angle here in green, that's the angle that the problem's asking for. If we wanted a true polar angle, we could solve for this angle out here in pink. Whatever you want to do there to solve for it will work. If we just do a quick little answer here, I'm going to use the inverse tangent. I'm going to use the 1.5 as my opposite side, and the 3 is my adjacent side. So I'm going to do the inverse tangent, and 1.5 over 3 is 0.5. So I get an angle here of 26.56 from the river current. If I wanted that on a proper polar angle, it would just be 90 minus that amount, which would give me the leftover down here of 63. So however you want to look at that, that's totally up to you. It's just another inverse sine problem, inverse cosine, inverse tangent problem. You've solved the triangle out. It's just what is it asking, okay? But that's it. That's how you can get a relative velocity here. It kind of makes a lot of sense because if you're standing on the shore and this river is moving like 1,000 miles per hour and you put a boat in, the boat's gonna whip by you at 1,000 miles per hour plus whatever the boat's doing with respect to how the vectors are positioned. So just taking something we already knew, something we already thought about, and just turning it into a more generalized situation. And as long as you keep track of what your objects are and what they're positioned relative to, or what their velocities are relative to, you're going to do fine on these type of problems. So with that, this problem is finished, and that pretty much wraps up all of Unit 4 there. At this point, it's just a matter of getting some practice, and soon we'll be able to move on to Unit 5, where we talk about projectile motion, because sea llamas go projectile! Either way, adios, take it easy, everybody.